Good morning all. Now that we have completed almost the entire portion of Geotechnical Engineering 1 as per the KTU syllabus, we'll try to revise through those portions using a few numerical problems explained in this video. Question number 1. A vane of diameter 75 mm and height 110 mm was used to measure shear strength of clay. It was found to have a failure torque of 600 Nm. Find the shear strength if the vane was fully immersed. So you have the vane shear test in which you apply the torque. The vane will have a diameter d and a height h, and the torque is given as 600 Nm. You're asked to find the shear strength if the vane is fully immersed. So the relation for shear strength when the vane is fully immersed is S equal to T by pi into d squared by 2 plus d cubed by 6, in which d is given, h is given in millimeters, and torque is given in Newton meters. So you'll have to have consistent units provided, and torque is 600 into 10 to the power of 3 by pi into d is 75, h is 110, and substituting will give you shear strength 0.503 Newton per mm square, or 503 kilopascals. I would suggest you to work all these problems on your own and try to see whether you are getting an answer similar to the one that is highlighted in yellow. Question number 2. What is the theoretical maximum dry density of a sample of soil with specific gravity 2.7 and optimum moisture content 16%? So we know that the dry density of a soil, rho d, equal to g by 1 plus e into rho w, where rho w is the density of water, which is approximately 1 gram per cc, and g is 2.7 as given in the question. Now, at theoretical maximum dry density, we explained during the compaction test that it will have saturation 100% theoretically. So I can write E to be equal to Wg by S, where S equal to 1. So the expression becomes rho d equal to G by 1 plus Wg into rho W, where water content is already given 16%, specific gravity is already given 2.7, and substituting you will get the answer for rho d as 1.88 gram per cc. Question number 3. A slope is to be constructed at an inclination of 30 degrees with the horizontal. Find the safe height of the slope. Consider a factor of safety of 1.5 and cohesion 15 kilopascal. Unit weight of soil is 19 kilonewton per meter cube, and the angle of internal friction is 22.5 degrees. So this is something related to the stability number, the Taylor stability number that we discussed, and Sn, Taylor stability number, equal to C by Fc gamma h. C is given as 15 kilopascal. Factor of safety is given as 1.5. Unit weight is given as 19, and the height is unknown. So you have 15 by 1.5 into 19 by h, and for the chart of stability number you have the data 22.5 degree angle of internal friction, and I, the inclination, as 30 degree. So from the stability chart, for I equal to 30 degree and phi equal to 22.5 degrees, you can have Sn approximately equal to 0.046. So from this chart you'll get Sn, and in this expression when you substitute the known value of Sn, you'll get the unknown value of height h, and solving, h has a value of 11.5 meters approximately. So any approximations that you take on the stability number will get reflected to the height that you arrive at, but nonetheless just try to see whether you are getting an answer similar to 11.5 meters. Next question. A trial slip surface AB is given. The radius is 19 meter. Weight of the soil in the wedge is 2050 kilonewton. The soil is pure clay of cohesion 55 kilopascals. Find the factor of safety. So you are given with the geometry in the question. You have a slope ADB with a failure surface AB, and the weight of the soil inside this wedge ADB is 2050 kilonewton as given in the question. Now this surface AB is assumed to be a part of a circle whose center is given as O and the radius is 19 meter, and the angle subtended at this center is 64.5 degrees. The extra data given in the question is that the weight W, 2050 kilonewton, is acting at a lever arm of 9 meter with respect to the center. So your intention is to arrive at the factor of safety. To start with, let's try to find the length AB, which we have marked as capital L while explaining the theory. So the length of the arc AB is nothing but r theta. Theta is 64.5 and r is 19 meter. The only thing that you need to take care of is to convert theta into radians. So converting that to radians by multiplying by pi by 180, you'll get 19 multiplied by 64.5 multiplied by pi by 180. So that turns out to be 21.39 meters. So that's the length of the curve AB along this failure surface. Now we know that the factor of safety is the ratio of moment resisting failure to the moment causing failure. So the moment causing failure is the one that drives this slope downward and outward. So downward and outward is nothing but a clockwise moment with respect to the center O. So that's 2050 kilonewton force acting at the lever arm of 9 meter. That is a moment causing failure. Moment causing failure, MO, or moment overturning, equal to 2050 multiplied by 9, which is 18450 kilonewton meter. And the moment resisting failure should obviously be something that's anti-clockwise. So when you think about this, you'll understand that the moment that resists failure is the effective cohesion that is mobilized along the surface AB. So cohesion acting along the surface AB will try to prevent the slope failure. So MR, moment resisting failure, equal to cohesion multiplied by the length of the arc multiplied by the radius. So C multiplied by L will give you the force, and it gets multiplied with the lever arm, which is nothing but the radius. So you have 55 kilopascals, the cohesion, multiplied by length of the arc, which we have obtained as 21.39 meters, multiplied by the radius, 19 meter. So moment resisting failure is 22353 kilonewton meter. So you have moment overturning or causing failure and moment resisting failure. Factor of safety is equal to MR by MO equal to 1.212. Question number 5. A clay sample 24 millimeter thick consolidated 50% in 20 minutes when tested in a lab with drainage allowed at top and bottom. The clay layer from which the sample was taken is 4 meter thick in the field. How much time will it take to consolidate 50% with double drainage? So you have a consolidation test data with you where a clay sample of 24 millimeter thick consolidated 50% in 20 minutes in the lab. So the drainage allowed is at the top and the bottom, which means that it's double drainage. Or D, the distance traveled, the maximum distance that a water particle have to travel is half of the thickness of the sample. That's maximum length a water particle should take. So that's 12 millimeters. That's a double drainage. Now, based on this data, the clay layer from which the sample was taken is 4 meter thick somewhere in the field. You're asked to calculate the time that the clay will take to consolidate 50% under the same double drainage condition. So you have an equation for time factor TV equal to CVT by D square, or time taken when cross multiplied equal to TVD square by CV. From this expression you can say that time is proportional to the square of the drainage path, or TV and CV remaining constant, T is proportional to D square, or T1 by T2 equal to D1 square by D2 square, where D1 is half the thickness of the sample that you have in the laboratory, which is 24 by 2, and D2 is half the thickness of the sample you have in the field, which is 4 meter by 2, that's 2 meter or 2000 millimeter to have consistent units. And T1 is the time taken in the laboratory, that's 20 minutes. So when you substitute D1, D2 and T1 in this equation, you can get T2 in minutes. So when you convert minutes to hours and then to days, you'll get 386 days. So that's a number of days which will take you to have 50% consolidation in the field for a 4 meter thick soil, the sample of which took 20 minutes to consolidate in the laboratory.